Okay, so welcome to Cloud Native Live. So where we dive into the code behind Cloud Native. So I am Shahriar, almost like a Mithil, so you can call me Mithil Shahriar. So okay, I'm a Sensitive ambassador, and I'll be your host tonight. So every week we bring a new set of presenters to showcase how to work with cloud native technologies. So they will build things, they will break things, and they will answer your questions. So in today's session, I'm stoked to introduce Mackenzie and Caleb, who will be presenting like from inner loop development to Kubernetes with the SpinKube. So this is an official live stream of CNCF, and as such is subject to the CNCF code of conduct. So please do not add anything to the chat or questions that would be in violation of the code of conduct. So basically, be respectful to all of our fellow participants and presenters. So with that, I will hand it over to Mackenzie and Caleb. So let me add them to the stream. Okay, so hey Mackenzie and hey Caleb. So how are you guys?
Hey there, I'm doing well. Super excited to be on the stream today, talking to all of
Yeah,
you.
yeah,
Yeah, doing great.
All right.
yeah, awesome. So I think you guys can start by introduce yourself, and then we can start our stream. Okay.
Great. All right. Well, hey, I'm Mackenzie. I am a product manager here at Fermion. And yeah, I'm really looking forward to talking to you all today a little bit about Spin, developer tool, and SpinKube, a tool for platform engineers to go ahead and run those applications alongside their Kubernetes resources. Caleb, I'll let you introduce yourself.
Cool. Yeah. My name's Caleb. I'm a software engineer at Fermion, and I'm also really excited to play with some SpinKube today and answer some questions.
Yeah, awesome. So let's get started and start our session. Okay. So yeah, let me add. Okay.
All right. Hopefully everyone can see my screen. And if there are any questions that come up along the way, do drop them in chat. We love to hear from the audience as we walk through this stuff. All right. So as you heard at the beginning, we're going to be taking a journey from inner loop development, working with a developer tool called Spin that allows you to write event-driven serverless applications that compile down to WebAssembly. We'll learn a little bit about what that means, play around with it, and then explore running an application that we built on a Kubernetes cluster with a separate project called SpinKube. All right. And if you aren't familiar with WebAssembly or Spin, that is more than okay. We're going to cover the entire journey starting at the very beginning. So do stick around. At Fermion, we like to talk about 3 different waves of cloud computing, just as a way to introduce people to the concept of WebAssembly if they aren't familiar. The first wave is virtualization, so the virtual machine. The first offering on AWS was EC2, really revolutionized the way folks were building applications. You could go and host your app on hardware that someone else owned and operated. From there, containers were the next massive wave explosion of technology. All of a sudden, we had a great way of packaging up our applications and distributing them across a variety of environments beyond their local host. And then the third wave that we've talked about and that we're most excited about here at Fermion is WebAssembly, which was a technology originally built for the browser that we're bringing server side with a tool called Spin. And it essentially allows you to write event-driven code that's very secure, very lightweight, and extremely portable. You can run it in a multitude of environments. So it's a great solution for applications that have low latency requirements, need to be portable, and we'll go into some of those benefits in a bit. But these are the 3 waves as we look at them today, and they're not mutually exclusive. Obviously, containers and WebAssembly run on top of virtual machines. They simply complement one another. And through a demo today, we'll kind of explore exactly how they do that in practice. So if you aren't familiar, just a high-level 3,000-foot view architecture diagram. Here we have code. So any programming language you would like, you can compile down to WebAssembly, which is essentially just a binary, an execution format, and run that application anywhere that supports a WebAssembly or WASM, which is the acronym runtime. So that could be on a multitude of operating systems, architectures. As long as it has a WebAssembly compliant runtime, you can run that application nearly anywhere. We'll be exploring 2 out of these 3 options today in our demo. So some of the benefits, if you're thinking about applications you've built in the past and you're trying to determine when WebAssembly would be a good technology to use, I would look at it through these lenses. If you have some sort of event-driven code that you really value portability, you want to be able to write and play with this locally, deploy to a multitude of different clouds, maybe run on edge without having to worry about making any sort of changes to your application source code, WebAssembly could be an interesting technology to explore. Because WebAssembly is just your core business logic and you're not bringing along a lot of the extra stuff that you typically get with containers, such as file systems and all that other stuff that gets layered in, layers literally, they're relatively small. So you can run many applications on the same host. So you'll often hear folks talk about density benefits. And what that really means is you can run a ton of applications on the same size virtual machine because all of a sudden you're working with much smaller packages. Sandboxed, so this is a legacy trait of being built from for the browser. WebAssembly components have linear memory, which means they can't access each other's memory systems, and have a denied by default posture. So when you build an application, which we'll do in a little bit, you have to grant your application access to things like being able to make outbound requests or connect to databases. So that's one of the benefits is you're really set up for success on day one when you're building these applications, and you have to be very conscious about giving capabilities back to the application. And then lastly, this comes up a lot is startup time. So a WebAssembly component can come up in less than a millisecond, which is why these functions work so well on the server side when you want to have really, really responsive applications that you aren't running 24/7 in order to meet those requirements. You can really, truly scale to zero thanks to how responsive they are. So now that we've covered a few of the benefits, and we talked a little bit on that previous slide of you can run a WebAssembly application as long as you have a compliant runtime, that is a great segue into Spin, which is a developer tool for building and running event-driven serverless WebAssembly applications. So a combination of a CLI that's going to allow us to scaffold an application, build it, serve it locally. It also includes a runtime, so that automatically gets installed on your machine, and a programming model. As you are likely familiar with functions, you typically run those with other services, whether it's a database, maybe containers. Functions tend to be used as glue code to pull a workload together that's using disparate parts. So there's a programming model that helps you do all of that. And it is an open source project, which is being contributed to the CNCF. So with that context, let's go ahead and do a really quick demo to take a look at it in action. And let me just pick the right terminal screen. Can people see my terminal okay? I see a nod from Caleb. That's great.
Yep.
Okay.
Good to go.
So I have Spin already installed. If you don't, it's fairly easy. There's a variety of ways to get started with it, brew, etc. On the developer docs. And what we're going to do is run a spin new command. And what we'll see is a list of templates that come by default. And they follow this naming convention where you have the trigger type at the beginning and then the programming language second. So Spin supports a variety of different programming languages. We can choose one today. Let's go with Go. And you can see at the bottom, some don't actually follow that naming convention, and that's because I've added them in. You can build templates, so you can share with others, perhaps a Spin application that's been useful and you want to add it to a larger application. That's something that's totally supported with Spin. So we're going to give this a name. Hello, CNCF Live, a description, do a hello world. And then the path. So this is the route when we are going to call the endpoint that will be used to hit the component within our Spin application. And if we take a look at what's in here, you'll see we have our main source code, and then we also have a file called spin.toml. This is our application manifest. It automatically gets scaffolded by the information we provided in that workflow. We can see our name, the description, our trigger, which we've chosen HTTP, and the route that it will follow in order to invoke a component. A Spin application is composed of one or more components. It's up to the author about how many you want to put inside your application, and you can handle traffic by providing different routes and even different trigger types in order to invoke your various components. So inside, we've started fairly simple. We just have our single component, and we have information like the build steps here that are required, and we'll explore this in a little bit more detail in a bit, but you can already see some of that capabilities-based security model where right now we don't have any allowed outbound hosts, so this application is actually not allowed to make any external calls as it's built right now. So let's take a look at this in action. We're going to run a spin build, which is going to build the application. And there's an up flag. So if you want to go straight from the build to serving it locally, this is how you can combine those steps in one go. All right, it's ready. And we'll go ahead and ping that to make sure it's working. Great. There we go. That was all it took to get started with our first event-driven serverless WebAssembly application. So we said we talk a little bit about inner loop development, and one of the cool features that is supported in Spin is dynamic reloading. So if you run a spin watch command, what's going to happen is we're going to be constantly rebuilding and serving our application. So if we want to make many iterative changes, we're able to do so. So we can see it's ready again. We can pop back over, and then let's make some changes and just see how that goes. We'll do something simple for now. Change the println statement to hello CNCF friends. And then we'll take a look. It should be watching and monitoring those changes. And if we curl localhost again, give it a second try, you see we've taken those changes and our println statement is different. So we didn't have to go ahead and rerun that build command. It's listening. It took a second, but this is a nice feature if you're making a bunch of changes and you don't want to have to constantly be building and checking the endpoint again.
And Kenzie, just so you know, I don't think we could see the second tab, but rest assured, and we'll show later in the demo that the curls were hitting that spin app. So.
Oh, okay. Thanks for letting us know. You'll have to explore it a little bit when you bring up our second application. Cool. So now that we have the basics of spin down, we explore the CLI, we've taken a look at the application manifest, all of that good stuff. We're going to upgrade to a slightly more complicated workload. And before diving into the architecture, we're going to actually look at the end product itself. It's a simple game that you can play in the browser called Finicky Whiskers. And the premise is you essentially choose an animal. You have two to pick from, whether you're a cat person or a dog person. I tend to lean towards being a cat person. And once you've selected your player, the timer starts going. You have 30 seconds to go ahead and feed this animal as much as you can correctly. So you see in the thought bubble, it's prompting for different types of food. And based on what it's asking for, you need to click the correct can. And it's going to change randomly at time, and you're going to do your best to feed it as much as possible in the 30 seconds that are allowed. So it's a good test of your reaction time. Once you're done with gameplay, a little bit of formatting error, but that's okay. There's a leaderboard on the right, and unfortunately, my 35 correct feeds was not enough to earn me a spot, but maybe next time. Cool. So now that we are familiar with Finicky whiskers, let's take a closer look at what's happening behind the scenes to actually make that game run. So beyond being a cute cat, that's not really the focal point of the game, although it's a lot of fun. It's really more a story about how we can rethink how we compose microservices. So during that gameplay, we definitely went over a few requirements. We need some ability to manage a session. So if multiple people want to play the game at the same time, we can support that. During a session, you need to be able to determine whether or not your player is providing the animal with the correct food. You need to keep track of the score. So over time, just making sure that score is updated and presented back to the player so they know, do they need to pick up the pace, or maybe they're cruising and they're already on their way to a high score. And then lastly, it might be nice over time to be able to reset the leaderboard for whatever reason. So with all those requirements in mind, Finicky Whiskers was built. It's composed of 7 different microservices, all of which are a component inside of a single Spin application. So that same application manifest we were exploring earlier has grown to support not just one component, but 7 to build something like we just interacted with. Some of the components are written in Rust, others in Go. I think there's one written in Ruby as well. So you can support a variety of different programming languages, and they're still all compiled and run together with the same build command, all within Spin. So you don't have to handle each service independently. You can really run them as one large application. And on top of that, we don't just have our Spin components, we also have external data stores. So we're going to be taking a look at the SDK and how we can go ahead and get connected to things like a relational database and a key value store in order to store state about our gameplay. And before we get into the code itself, I'll do a really quick overview of each of these services just so we have a high-level understanding. There's a session manager, which is going to go ahead and start the game. It keeps track of a timer, and it also keeps track of the animal's changing preferences. As the player starts to interact, we have a tally service that's going to register each food click, verify whether it was successful, / asked for fish, you provided fish, or perhaps it wasn't, and it's going to send those results to a key value store. The scoreboard is what we saw, that number in the top right, where the number gets presented back to the user. It's reading it from that key value store, so the user understands exactly how well they're doing. At the end of the game, there is a high score component that's going to evaluate whether or not the player was a high score player, and if so, they're going to get an opportunity to store a 3-letter acronym in their score to be presented inside of the leaderboard. Reset, so if we wanted to reset the session, that's going to be supported. And then there's also a file server that it has a bunch of static assets that will be served to the browser. So if any of these services need an asset, it's all stored within that file server. And I believe it has in excess of like 30 plus assets that it's going to be sending to the browser over time. Cool. So that was a lot, but hopefully you have a good understanding of the different services and the premise of Finicky Whiskers. And one last little fact about the game. It's really meant to be a story of load generation. So as you're feeding the cat or the dog, you're invoking our Spin application. In a typical gameplay, we're going to see around 200 requests or more of the application being spun up and spun back down. So it's a good example of how you can build something that runs when it's not being needed, but respond really well and very quickly in a game that you need to have the tally updated quickly and generate a lot of load. So now that we have an idea of what the architecture of this application looks like, Caleb's going to go ahead and explore exactly what the application manifest looks like and serve it locally using Spin. So with that, I'll hand it over to Caleb.
Absolutely. Thanks, Kenzie. And I just want to acknowledge Vijay has put some really good questions about SpinKube in the chat. I think maybe we'll hold those questions just for a second here before we dive into the SpinKube material. But those are great ones and some good talking points we'll cover here in a second. Okay, so I'm gonna talk a little bit more about the Finicky Whiskers application here, and specifically kind of dive into the application manifest, understanding that, looking at some of the code, and then also playing around with different data sources and runtime configuration. So as Kenzie said, we've got this spin.toml, which is our application manifest. And really, there's kind of two important parts that you'll find in an application manifest. You're going to find triggers, which is like wiring up events from the outside world to be pointing at the other important part of an application manifest, which is components. And so these triggers are configuring, for example, in this case, HTTP routes. And so we have tally is a great example. Anytime a request comes in on the tally route, we want it routed to the tally component. Similarly, anytime something comes into the high score route, we want it routed to the high score component. Okay, so that's what triggers are doing for us. And then, what does the configuration of a component look like? Well, we've got a couple different parts within a component. We'll look at high score because that's a good example here. So, we've got the component, we're defining a name, and we're defining some source for that component. And so that's really just saying, where does this WebAssembly component live? What component am I executing? And the way we're actually creating this highscore.wasm component is we're running spin build. We saw that demoed by Kenzie. And so here we can define what the actual command is. And the nice thing about this is we can completely abstract away from the tool chains of all the different languages for how you compile to WebAssembly. You don't need to know, what specific flags do I pass for compiling something to WebAssembly in Rust, or how to do package this up in JavaScript. We template that out for you, and then you can just run spin build, and it will automatically create that component. Some other relevant things here are we're also seeing things like allowed outbound hosts or key value stores or SQLite databases, things like that. And so this kind of fits into the component capabilities-based security model of WebAssembly, where by default, the WebAssembly component has access to nothing. And so you need to explicitly provide access to different things. So we'll be coming back to this and kind of talking more about how this works and what the labels mean and what that gives us. But I want to dive into some code here. So if I pull up the high score component, this is one of the components in our Finicky Whiskers application. In this case, it's written in Rust. So here we're using the Spin Rust SDK. We won't be going fully into the code here, but kind of giving you a high-level overview of what's going on. We've got our kind of main function here. And this HTTP component macro is automatically wiring this up so that when this WebAssembly component is executed, your high score function is executed. Then we're doing kind of traditional, HTTP routing stuff you would be expecting to happen. Is it a get method request coming into this application, or a post method, those kinds of things. And then from within there, we're doing things like checking the high score and getting the high score. And so this is a bunch of business logic. We're parsing the incoming request body. We're interacting with the database. Here's an example of that, where we're running this specific query against our SQLite database, where we're persisting the high scores. And so the Spin SDK makes it super easy to interact with these kind of resources, either the key value store or the SQLite database. You can see we're using the Spin SDK here to create a connection. And then we're executing that against the database. So, this kind of gives you an overview of what it looks like to build a Spin application in, your chosen language. But what I want to highlight a little bit more is this concept of opening a connection. So I mentioned earlier, there's capabilities-based security, and we have to explicitly define we want access to a database. And so we can see we're in the high score component, and the high score component has access to the default database. If I were to remove this and we were to run the app, and I can show this later, we'll show this error later, we would get an error where it's saying, oh, I can't do that. I don't have access to that database. But we're giving access to the default database here, and so that works fine. But a really interesting thing is happening here where we're using labels. And so what does it mean to get access to a default database? Well, As an application developer, I don't really care where my database comes from. All I know is that I want to have a SQLite database where I can shove my values, and I want to make sure that that fits my needs in that way. But I don't really care about provisioning that database. I don't really care about managing the life cycle of that database. And so this concept of like labels lets us decouple these two things. And so as an application developer, I get to use this application manifest, which is really for, when you're thinking about building your application, and say, give me a default database. And then operator, later we'll see, the Kubernetes manifests where you would actually define the kind of backing implementation of this database. And that's how we kind of like decouple those two things. So let's just run the application here. So if I go, if I go spin up, oh, I went too far back in my history. Let's try again. There we go. Okay, so we will run this here. And actually, just to quick demo first, I can run spin build, which is going to rebuild all the components here. And so we'll see all sorts of different tool chains running. We've seen, like our file server packaging things up. We've seen Rust compiling different things. We see some JavaScript stuff using Webpack to package all the things up. And then if I run up here, we got the service going. Takes a second to load here. And I can pull up this, and we can go to localhost 3000. All right, I must have done a debug build or something because it's taken a second.
In the meantime, while we're waiting, I know Vijay had a question specifically about SpinKube, but I think looking at
We'll take
Spin,
that
I mean,
right now.
Oh, sorry I didn't quite get that. Could you repeat that?
Oh yeah, I just mentioned because we have few questions about like SpinKube, right? So I thought maybe we will take it at the end, but are we going to take that right now?
Yeah, I think Kenzie's saying one of
them
them is pretty applicable to the WebAssembly stuff. So take it away, Kenzie.
Yeah, I just wanted to tie a thread, and we'll get to them maybe at the end in more detail around the context of SpinKube. But Caleb did a great job illustrating WebAssembly is these applications are stateless, but we explored how you can connect to an external database and persist state there, and that will continue to build as we talk about the orchestrator later.
Absolutely. And when we get to the SpinKube stuff, we'll show how you can like mount volumes and configure that all in the SpinKube context there. Yeah. Awesome. So we've got it running here. And so, same game before, we can run this here, and we'll see all the logs going locally. But let's say, so when I'm running this locally, right, we're storing things into a SQLite database. So where is that going? In the case of running Spin locally, it's automatically just kind of bundling in a SQLite database with Spin, and it's like storing it in a local directory for you. And then the key value store is just automatically also backed by a local SQLite database. But let's say for my local testing here, I wanted to try putting this in some remote SQLite database. Terso is a company that offers remote SQLite databases. So I've spun up a database with them, and you can use something called runtime config.toml. So I'm sharing some secrets here. So, this database will be deleted at the end of the presentation. But this runtime config toml is allowing us to say, okay, for the default SQLite database, I want you to use a remote libsql connection and connect to this database. And instead of using the local one, we'd be using that remote connection. So I can just briefly show what that would look like. All right. Perfect. So we've got that going. And now, right, we're running with the same application here, but now it's actually backed by this remote SQLite database in Terso, and we'd be able to put values into that database. Okay, perfect. So now I just want to show one last thing before I hand it back over to Kenzie here, which is when you're running in production, and even locally for kind of debugging stories, it's often handy to be able to do like tracing of your application. The community's kind of coalesced around OpenTelemetry as kind of a standard for that. And so Spin actually has support for that. And so you may have caught that I'm doing a sleight of hand here, and I'm not actually running Spin up, I'm running Spin OTel up. And so Spin OTel is a plugin we have that just runs Spin up with the correct configuration to export traces out to like OpenTelemetry collector. And so I've also previously run Spin OTel setup, which is running I guess I can just show that, is running a open telemetry collector and Jaeger and a bunch of other backends and Grafana to explore all that information. And so by running this here, we can just see that will generate some traces. So I'll play a game here. We'll play as Ninja, and we'll eat some veggies. Perfect. And then we'll go to Jaeger here, and we can see that we're generating traces. So if I just go back in the last 5 minutes and find traces, we can see we're getting lots of GET requests to score components, all sorts of things like that. But let's just take a look and explore the high score component. So posts to high score. All right, we see none, which makes sense because we have not yet finished the game. But in 3 seconds here, we will finish. Perfect, and that should fire off a post. And there we go. Okay, perfect. So we've got this post request here. We can see a post request was made to the high score endpoint. A WASM component was executed, the high score component, and then all sorts of things are happening. We're opening the SQLite database. We're running this query. We're running that query. All sorts of things are going on. And then just last little piece to demo here. If I were to go into the spin.toml and I were to remove access to the default database, and then I were to run this and go here, play the game, play as Ninja. Perfect. Fortunately, we have to wait the 30 seconds. But what we're going to see, right, we'll think about what we expect with the capabilities-based security. It's going to try to open that database from within the component, but it's going to fail to open that database because we've locked that down. And so we'll be able to see that in traces here in Jaeger, and that kind of just makes the whole debugging experience a little bit easier. Kenzie, I'll hand it over to you. I'll show the last few seconds here of the error on the screen, but I'll hand it over to you.
Sounds good. Let you pull up that error really quick.
Awesome. So I think it failed. Yeah, there we go. Perfect. And we can see the error right here. Error access denied. Perfect.
Nice. Broken the way we expected.
Exactly.
And another thing to consider there, since we have multiple components in our Spin application, is it's access granted by component. So you revoked it from that one component, but if another component still had that default database line in the app manifest, it would continue to function as expected. So there's definitely granularity that you can apply controls to within your Spin application itself. But wrapping up that specific section, Caleb, thanks for showing us Finicky whiskers locally. It's cool to see all of those components working in concert, and you were able to get a high score with your local leaderboard. Now we're going to move on to the second half of this talk. So we focused on kind of inner loop development, making changes, building, viewing, observing our application locally, and we're ready to take that next step and run Finicky whiskers in a more production-like scenario. Let's imagine maybe we want to run multiple replicas of this application to increase our availability, or perhaps it was really nice that Spin already provisioned us a SQLite database out of the box to use, and that's great, but now we want to run on a larger stage, have people play the game, and perhaps we already have data stores provisioned in a cloud, like a Redis instance that we would like to connect this application up to. In order to do that, we're going to need some sort of orchestrator or tool to do so. And that is where we're going to go ahead and take a look at SpinKube. I'll bring my slides back up so you can take a look at the same time as me. SpinKube is a project that allows you to run your Spin applications alongside your existing Kubernetes workloads. Basically, the foundational work from this project comes from the fact that we've removed the container entirely. We're going to take that same Spin application that we had locally and package it as an OCI artifact, which means we're only going to be shipping the compiled application and its assets without any of the system dependencies. In order to run that application alongside your traditional pods and other resources, we're going to need some help, and that's going to come from a shim. The containerd spin shim is going to use a technology called runwazi to go ahead and inject the WebAssembly runtime and allow you to run that alongside your traditional pods on containerd. So you can have a worker node that has mixed pods and Spin applications. And then if you don't want to go ahead and have to manage that shim yourself, I don't blame you. That's where Runtime Class Manager, formerly known as KWASM, comes into play. It's an operator that's going to go ahead and install the shim on the desired hosts, manage version lifecycles of the shim, patches, all through the Kubernetes API itself. And then lastly, most importantly, we have an operator, and that's what's going to be taking these Spin applications, which in the world of Kubernetes are represented as custom resources, and manage deployment, scaling, routing traffic to it, all of that good stuff. And I guess taking a step back, why Kubernetes? It's just become an industry standard for orchestrating microservices. And so we wanted to come together and build a project that allows you to run Spin alongside the workloads that you already have in practice today that would benefit from using server-side WebAssembly. To circle back to Finicky Whiskers, you could imagine if we built that application with pods, we had 7 microservices, each one of those being its own pod. If you're running 2 to 3 replicas, you could have 14 to 21 pods. And we're going to now shrink that footprint down to one single Spin app that's a custom resource that will be deployed and managed with SpinKube. This is just a slightly different way of looking at these projects. We have a plugin that we won't explore today, but if you've already used Spin and you have some applications that you're interested in running on SpinKube, you can use that to convert the spin.toml into the custom resource YAML without having to scaffold any of that by hand, and then hand it over with a kube control apply to a Kubernetes cluster that has SpinKube already installed. Should also take a beat and say that SpinKube is being contributed to the CNCF and is the culmination of the work of a lot of different people coming together and trying to create a great end-to-end experience for deploying WebAssembly-based workloads on Kubernetes. So that's the high-level view of the different projects that come together to build SpinKube. And let's look at it in practice. And we're going to take our Finicky Whiskers Spin application and go ahead and actually deploy it to a Kubernetes cluster using this technology. Caleb, do you want to take it away?
Absolutely. I thought maybe now would be a good chance to address the question about supporting event-driven architectures within Kubernetes. I think, and I'm curious what you would add to this, Kenzie, after, but I think it's such a good fit because Spin in itself is so good at supporting those kind of event-driven architectures with its performance and ability to scale up and down, and no need to like provision a bunch of spins waiting around because you can just scale the components up right away. And then the way I tend to think about it is that SpinKube just allows you to, whacking my mic here, allows you to mold the kind of advantages of Spin directly into Kubernetes where you're running the rest of your things. And so we'll also chat a little bit in once I do my demo here about some of the auto scaling things we can do with SpinKube. But that's what I would say. Do you have anything to add, Kenzie?
Yeah, I think elasticity and ability scale is a huge reason why WebAssembly is a good fit for running on Kubernetes. And the experience is very similar to the one we just described, right? Application developers are going to define triggers. We recently had a community contribution for an AWS Kinesis trigger. And so you just write the application to handle that business logic, and it can be deployed and invoked on your Kubernetes cluster without having to, if you don't want to set up Kata scaling and you want to just continue to use your custom, those triggers, that's something that you can do fairly seamlessly.
Right.
So,
and if you do want to add something like Kata scaling, because we're not packaging in, I'm getting ahead of myself because I'm excited answering this question, but because we're not packaging in the operating system and the runtime and all of these different things, we're drastically simplifying what it takes to start up one of these pods running a WebAssembly application. And so we're able to scale out quicker than you typically would see with a more heavy duty application that you might be running. Okay, so I think I'm sharing my screen. We can swap over to my screen here. And I'm going to chat a little bit more about some SpinKube stuff. So for the purposes of this demo, I went ahead and set up an AKS cluster, just as an example of a place you could run a Kubernetes cluster, but SpinKube can run, in K3D, EKS, wherever you really have a Kubernetes cluster and want to run it. We'll be breezing over this for the sake of time, but we have great documentation at spinkube.dev for installing the spin operator and all the necessary projects to run SpinKube in your cluster. The key parts here are you install the spin operator and its associated custom resource definitions, which we'll be exploring a little bit more here and understanding. And then you need to set up the runtime classes. And so these docs are still using the KWASM, but soon they'll be swapped over to Runtime Class Manager. And this is just making sure that the appropriate containerd shim is living on each of the nodes in your cluster. Great. So that's what it looks like to install the spin operator, and we've got Helm support for that. Let's poke around in the cluster. I'm going to be using K9s for most of this. Resize that. Perfect. K9s is one of my favorite pet projects. It's great for exploring Kubernetes clusters with. Perfect. Okay, so we've got our cluster here. It's just a small AKS cluster with 4 nodes running here, and we've got a whole bunch of different pods. We've got all sorts of networking and cert manager stuff going on here. But the interesting part here is we've got the spin operator controller manager running. And this is handling all these custom resource definitions. And so we've got our Finicky whiskers application. We want to bring it to Kubernetes. What does that actually look like? Let's go look at the code. So we've got a custom resource, and that custom resource is called a spin app. And so this is how you actually package up your spin application and then run in Kubernetes. So you give your spin app a name, and then this is probably the most important line of the specification. So this is saying, point at the OCI artifact where that WebAssembly is stored. And so prior to this, you would spin build your application, and then you would run something like spin registry push GitHub container registry.io your tag or whatever like that. And we'll be demoing this a little bit later when we talk about some artifact analysis stuff. But this will package up and push your image to a registry. And again, I really want to hammer this home. It's only going to be including the WebAssembly components that you need to execute, along with any like static assets you're serving. And so you're not packaging around and carrying around all of this kind of heavyweight runtimes and operating systems. Then the executor is just saying, use the containerd shim spin to execute that. It's kind of outside the scope of this presentation, but you could use this to point to different kinds of executors for ways to execute your WebAssembly application. We talked about, auto-scaling. So this is allowing auto-scaling to happen. So you can do things like hook up, an HPA or a CADA auto-scaler to this and scale automatically your application based off the amount of load it's generating or the number of messages in queue or things like that. We provide all sorts of other kind of like primitives that you might expect to find on something like resources and things like that. And also to the point of what was the question here? Limitations with managing stateful applications in Kubernetes. We do also provide the ability to like mount volumes, so you can access like the file system if that's an approach you want to take. Or we'll get into runtime config here, and this talks about how you can configure different backing data stores for your application. Okay, so I've already got this applied into my cluster, and so let's go ahead and take a look at it. So we'll see if I go to spin app custom resources, I've got a Finicky spin app deployed here. It's got all the values we would expect to see. And so what this actually maps down to is that this maps down to a deployment. So we can see that a deployment was created, and we have the default number of replicas, which is 1. And so if we go to this deployment, we'll see that we have 1 pod running. We've got the logs here, and we can see we're getting tally logs and people requesting all sorts of different static assets and things like that. Great. So what is this runtime config? How does this work? This is just kind of like this runtime config we did in the local scenario, where we were able to configure different backend databases for the key value store and the SQLite database. And so that's the same thing translated into this kind of custom resource definition. So we'll focus on the SQLite database first. we're going to be providing the default SQLite database that we were referencing earlier, and we want it to be using a libsql database that is has credentials defined in the Terso database secret. So I just created a secret in the cluster earlier that has these credentials. And then similarly for the key value store, we want it to be backed by Redis this time, and its credentials are defined in a secret. And so we can just see earlier that if we go to all the pods and I just search for Valkey, we're running Valkey, which is like a fork of Redis to provide that backend for the key value store. And so that's where that's being stored. Again, I really just want to drive home the point of like, this is, separate. So we use the term manifest a lot, right? But we've got the spin.toml, the application manifest, that's really good for an application developer to think about. And they just have to think about, I want a default database and I want a default key value store. And then the operator gets to think about this kind of Kubernetes manifest and think, okay, how am I going to provide this default store, this default SQLite database for the user? Awesome. So we've got that going, and I actually have this cluster live. We've got some ingress and routing set up for that. So I'm going to share a link here, and people can go check this out if they want. I'll put it in the private chat there, and maybe someone can add it to the main chat. I'm not quite sure how to do that. But yeah, if people go to finicky.fermion.technology, this is running our Finicky whiskers application on the live cluster. And so people can go check that out. Maybe we can take a chance to answer some of the questions here, Kenzie. So I feel like, we've talked about how do we address the limitations of stateful applications, things like we provide the ability to do like volume mounts. We also provide the ability to wire up different backends for databases or key value stores. In the future, there's plans for WebAssembly to support things like S3 object storage natively, so you can configure that with your application. And that's what I would say to that.
Yeah, I think
And
that's...
sorry. I was going to say, if maybe do you have anything to say on the question about managing WASM deployments different from traditional containerized services in Kubernetes?
Yeah, I think that's a good question to highlight. And hopefully it's become a little bit clearer as we've explored the Spin application custom resource. But really the gist of it comes from, we're deploying, as Caleb mentioned earlier, the OCI artifact. So we just have our WebAssembly components and static assets. It's much lighter weight than pulling down an entire container, which is going to likely be larger in size, having to mount the image, start the container, load the application, initialize it, get the pod ready. There's a lot more steps that are required, and there are certainly use cases. Perhaps you have heavy I/O, or you do really need, access to an entire file system. The traditional pod might be the right way to go for that particular part of your workload. But for something that is going to really be invoked only when you need it, when a certain event has triggered it, this is where Spin could be interesting. And the number of steps to deploy it are more condensed, right? You're just pulling down that OCI artifact, which is cacheable. You're loading the WebAssembly module into memory, that's cacheable, and then starting your really lightweight application. So you've really pared it down to just what you need in order to serve that very specific request. So hopefully that helps kind of juxtapose those two experiences of regular containers and then Spin app artifacts.
Absolutely. And I'll just share this link. I think this is a great article to go read. We talk in this blog post on the SpinKube website about the kind of difference in the process of running a full container versus just running an artifact. And so that might be an interesting thing to go read. I also just wanted to address the question, how does SpinKube optimize WebAssembly workloads across multi-cloud environments while leveraging CDN integrations? So I think there's kind of two parts here we can tackle. There's like the whole leveraging CDN integrations, and there's the multi-cloud environment. What I would say to the multi-cloud environment is, in some ways, it's kind of the same story as like any other Kubernetes resource, because we're just using a custom resource definition. So any of the projects you're using for like cross cloud I guess I'm actually thinking multi-cluster. So we support kind of multi-cluster scenarios natively there. But in multi-cloud, again, it's the same deal. And the beautiful thing about this is because you're not compiling this container down to x86 or ARM or whatever, you're not locked into running into certain nodes. And so if you have a AKS cluster running ARM nodes here, and you have a Linode cluster here running x86, you can easily just run this application in both places because it's just WebAssembly. And as long as you have the shim in both those places, it's going to run in both those places. So I'd say the multi-cloud story is pretty much the same as anything else Kubernetes, if not slightly better because of this architecture portability we have. And then also with CDNs, so we don't have any like direct integrations with CDNs with Spin, but you could definitely like back your CDN with a Spin application. And I think that would be like a great use case for this with all the kind of like serverless benefits we've talked about. And I'm sure Kenzie has things to add on both multi-cloud and CDNs.
Yeah, the only thing I'd tack on to multi-cloud there is the separations of concerns we've been exploring, in addition to just inherently the benefits you get around portability because we're using WebAssembly as a runtime. There's additional, portability that's kind of baked in the application manifest that we've built for Spin applications, where Finicky whiskers is accessing a key value store. And we can run that in a variety of different places and have it backed by many different key value stores as we're exploring today without any rewrites. So there are just some operational gains that you're experiencing from that level of abstraction when you're writing your core business logic that makes it easier to plug it in to different backing technologies, which definitely helps when you're considering things like multi-cloud deployments. And then, Caleb's answer to CDN is great. I think it's Spin's great use case for, grabbing content, modifying content, serving content, and event-driven workloads. So if you're able to run Kubernetes there on whatever Kubernetes distro you have, you can deploy SpinKube and serve up your Spin apps as well. There's a lot of flexibility, but there's still, I think you have to be on the latest version. There's a specific version of Kubernetes and Containerd that's supported. But other than that, the door is pretty open for where you can run these workloads, and all that information is discoverable on the spinkube.dev docs as well. But these are great questions. Thanks for sending them over.
Totally. I was going to say that too. Great questions. I'll stop sharing here and hand it back to you to talk about SBOMs, Kenzie.
Cool. All right. We've had a journey. We learned about Spin. We built our simple hello world, and we've progressed all the way through deploying a more complex microservice application to a Kubernetes cluster. We're going to take a step back and ask a question around Spin and how well it integrates with existing cloud native tooling. So a question that came up recently in the Spin community was, I have, an entire tool chain already set up for image scanning for my traditional containers. And is this something that I can simply plug my Spin applications into as well? And the answer is we're getting a lot closer with the ability to run Spin applications as OCI artifacts. So we'll take a look with the time we have remaining today on how you can generate a software bill of materials or SBOM artifact and go ahead and attach that to your Spin application. If you're not familiar, SBOMs include information on license, dependencies, versions, patch status, and you can use them to track vulnerabilities, audit software, identify risks, all of that good stuff. And so while using WebAssembly gives us a lot of great benefits and a strong security model, we're still importing packages, right? Where there are things that are coming into our code that we haven't written directly ourselves. So being able to scan that for vulnerabilities and understand exactly, what's going on if you need to address anything is an important practice to do. So that's what we're going to take a look at today. I'm going to go ahead and share my terminal again. And I don't think I need to switch tabs, so we should be good here, but holler if you lose visibility on what I'm doing. Okay. So we're in our directory with Finicky whiskers, same application that Caleb's been exploring today. And what we're going to do is use a tool called Trivy, which is an open source security scanner to generate our SBOM. To do that, we need to pass in the format that we're going to use. So there's a bunch of different formats that are used. SPDX is one of the more common formats that is used and recognized by the Linux Foundation. So that's what we're going to go for today. And then we are going to name our file. And what it's going to do is going to look at all of the files that we have inside of that Finicky whiskers directory and scan them for any vulnerabilities. And now if we take a look, we should see we do have that sbom.json file. And we can also use Trivy to scan it. So let's take a look at what's going on and see. Okay, so we do have a few vulnerabilities that we need to take a look at from Node.js. Also something in our cargo file as well. And that's all really great information to have. And I should say we're running this manually today, but best practice would be certainly to automate this in some fashion so that you're scanning on a regular basis. Trivy as a tool is able to integrate with GitHub Actions and Kubernetes operators. There's a lot of ways you can plug it in order to have it run automatically rather than manually as we are today. Cool. So this is good information to have, and we definitely have some action items we need to take out of this, but it would probably be most useful if it didn't live just locally on my machine, but it was discoverable everywhere our OCA artifact went. In order to do that, we're going to use a tool called Auras. Auras is a project that allows you to push and pull OCA artifacts to and from registries. It assumes that basically the media type is going to be anything but an image. So it is really built for OCI artifacts, which makes it a great asset to use to do things like attach an SBOM to a Spin application. So to do that, I already have Auras installed, but we're going to run the attach command. And actually, I can't do that quite yet because I haven't created a OCI artifact of my Spin application. So in order to do that, I'm going to do a Spin registry push, and I will provide my registry name and catch the typo in real time. And there we go. Okay, so what we do what happens behind the scenes when I run this command is it's going to go ahead and take my Spin application and push it up to my registry that I provided with the name and the tag, which is great. You don't have to author your Docker file or author that manually. You can just simply use the Spin registry push, and it's going to take care of all of that behind the scenes. And this is an important step to do because without having that OCI artifact, there's no way that you could attach the SBOM to it as well. So we're going to go ahead. And it looks like I had an issue pushing this one up. Let's see, what did I can do some real-time debugging to see exactly what went wrong on this one.
Yeah, we're breaking things as promised. Maybe just try again. That looks maybe kind of just like a random network error.
Yeah, I'll try and increment it again. And we'll see if that maybe it simply timed out on that one. And we'll give it a go. While we're waiting, we'll just take a look if there are any other questions. Doesn't look like it right now. We'll give that a few more minutes to go ahead and push up, and fingers crossed we don't time out on that one. If not, maybe you can go ahead and see if there's another OCA artifact we can run these steps on. Okay, there we go. We have success. So now that we have our OCA artifact, now we can run the attach command. So we're going to provide that information, the correct version number, and then we pass the file. So that's the SBOM that we generated, and then the artifact type as well, which there's a specific artifact type because this is a use case for OCI artifacts. And so what's cool, we're not actually modifying the, I got my version number wrong. We're not modifying the spin application at all. That is totally the same. What we're doing is pushing up a separate artifact for our SBOM, and it's being attached to our spin application as an accessory. And an accessory is a concept that was introduced by the OCI specification that allows you to store additional data or OCI artifact without having to make any changes to it. So it's essentially linking these two things together. So you can see we've gone ahead and uploaded it, and that all looks good. And we see that our SBOM is stored under its own hash. And then later on, if someone, let's say Caleb, wanted to work on Finicky whiskers later, he could use auras to go ahead and pull that down. And he would also be able to store that SBOM in a separate directory and explore it as well. So that's a way you can just track exactly what's going on with your software and your spin application as you distribute it in multiple places. So a great step forward. You can also use cosign to sign these and attest these as well. So just an example of how you can start to treat your spin applications very similarly to the other traditional pods that you might have running in Kubernetes as well. And then that is it for the scanning. Thanks for joining me on that journey.
So, yeah, so I think we have actually answered all of the questions, right? So yeah, thank you, Vijay, for your questions, so that they were very relevant to our topic today. And yeah, he has also, thank you guys for the proper answer and the demos, right? So yeah, thank you so much, guys, for the awesome session, right? So I think with that we can end our session because we're already out of time, right? So yeah, thank you so much, Caleb and Mackenzie, for an awesome time, and we really enjoyed your session for today.
Thanks for having us.
Thanks. This was great.
Okay, so great. So yeah, thanks everyone for joining the latest episode of Cloud Native Live. So we enjoyed the interaction.